What if I told you that right now, at this very moment, the sun could vanish from the center of our solar system, and Earth wouldn't know about it for over 8 minutes? Not just the light disappearing, not just the warmth fading, but gravity itself. For 8 glorious, terrifying minutes, we'd continue orbiting a star that no longer exists. And then, suddenly, catastrophically, we'd be flung into the darkness of space at 67,000 miles per hour with no warning whatsoever. But here's where it gets absolutely mind-bending. For nearly 3 centuries, scientists believed something completely different. They thought gravity was instantaneous, that it traveled infinitely fast, that the moment the sun disappeared, we'd feel it immediately. Isaac Newton himself built his entire theory of universal gravitation on this assumption, and it worked perfectly for predicting planetary motions, calculating tides, and sending rockets to the moon. So what changed? Was Newton wrong? Does gravity actually travel faster than light, or exactly at the speed of light? Or does it not travel at all? And here's the really disturbing question that kept Einstein awake at night. If gravity travels at the speed of light, why doesn't the Earth orbit where the sun was 8 minutes ago, instead of where it is right now? Because if we're responding to the sun's gravitational pull from 8 minutes in the past, our orbit should be completely unstable. We should have spiraled into the sun or been flung into space billions of years ago. The answer to this paradox is so strange, so counterintuitive, that it fundamentally challenges everything you think you know about cause and effect, space and time, and the very fabric of reality itself. And I'm going to prove it to you using nothing more than thought experiments you can understand right now in the next 230 minutes. By the end of this video, you won't just know whether gravity travels faster than light. You'll understand why that's actually the wrong question to ask. And that realization will change how you see the universe forever. Before we dive into this rabbit hole of space-time, reality, and the nature of causality itself, do me a favor. Hit that like button right now. Not later, right now. Because this video took months of research to create, and YouTube's algorithm needs to know whether this content is worth showing to other curious minds like yours. And subscribe, because we're going deep into the most fascinating questions in physics on this channel. Drop a comment telling me what country you're watching from and what time it is right now. I want to see how gravity is keeping all of us connected across this spinning planet. Are you watching from Brazil at midnight? Japan during your morning commute? Germany on your lunch break? Let me know. Let's build a global community of people who aren't satisfied with simple answers. Now, let's shatter some assumptions about reality. To understand whether gravity travels faster than light, we first need to understand what we even mean by gravity travels. And this is where most people get tripped up immediately, because we use the word gravity to describe 2 completely different things. And this confusion has persisted for over 100 years. Think of it like this. Imagine you're texting a friend. When you hit send, that message travels through the air as electromagnetic waves at the speed of light. There's a signal that propagates from your phone to a cell tower to your friend's phone. We can measure how fast that signal moves. But now imagine instead that you and your friend are connected by a taut rope. If you pull on your end, your friend feels the pull on their end. Is something traveling along that rope? Well, yes and no. The tension in the rope is always there, but disturbances in that tension, waves in the rope, travel at a specific speed determined by the rope's properties. Gravity works kind of like that rope, except the rope is space-time itself, and this is where things get weird fast. Let me introduce you to the first scientist who really grappled with this problem, Pierre-Simon Laplace, a French mathematician and astronomer working in the late 1700s and early 1800s. Laplace was trying to explain the motion of the moon with extreme precision, and he noticed something troubling. If gravity traveled at the speed of light, and the moon was responding to Earth's gravitational pull from where Earth was about 1 second ago, that delay should create a drag on the moon's orbit. Over centuries, this drag should be measurable. But it wasn't there. Laplace did the calculations and concluded that if gravity had a finite speed, it would need to travel at least 7 million times faster than light to be consistent with observations. 7 million times. That's not just faster than light. That's so fast, it might as well be instantaneous for all practical purposes in the solar system. So for over a century, the scientific consensus was clear. Gravity is instantaneous. It doesn't travel. It just is. When the sun moves, every planet in the solar system responds immediately, not because some signal travels from the sun to each planet, but because the sun's gravitational field fills all of space simultaneously. This made perfect sense within Newton's framework. In Newtonian physics, space and time are separate, absolute things. Space is like a giant, unchanging stage on which objects move around. Time ticks forward at the same rate everywhere in the universe. And gravity is a force that acts instantly across any distance. The sun pulls on Earth, Earth pulls on the moon, and these pulls happen now, not 8 minutes from now, or 1 second from now, but exactly now. But here's what will blow your mind. This entire framework, which worked beautifully for calculating everything from cannonball trajectories to planetary orbits, was based on a mistake. Not a small mistake. A fundamental misunderstanding of what space and time actually are. The first crack in this foundation appeared in 1887 in a basement laboratory in Cleveland, Ohio. Two physicists, Albert Michelson and Edward Morley, performed what's now considered one of the most important failed experiments in the history of science. They were trying to measure Earth's motion through something called the luminiferous ether, a hypothetical substance that was supposed to fill all of space and carry light waves the way water carries ocean waves. The logic seemed airtight. Light is a wave. Waves need something to wave through. Ocean waves move through water. Sound waves move through air. Light waves must move through something. Scientists called this hypothetical medium the ether, and if it existed, Earth must be moving through it as we orbit the sun. And if we're moving through it, we should be able to measure that motion by comparing the speed of light in different directions. Michelson and Morley built an incredibly sensitive device called an interferometer that could detect differences in the speed of light to within a tiny fraction of a percent. They measured light traveling in the direction of Earth's motion through the ether and light traveling perpendicular to Earth's motion. The speed should have been different. Earth's motion through the ether should have created an ether wind that affected light. Speed, just like a river current, affects the speed of a boat traveling upstream versus downstream. But the experiment showed nothing. No difference. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. They repeated the experiment at different times of year when Earth was moving in different directions. Still nothing. Other scientists repeated it. Still nothing. This was a crisis. Either the ether didn't exist, which meant light waves were somehow waving through nothing, or space and time behaved in ways that were far stranger than anyone had imagined. Enter Albert Einstein in 1905, a 26-year-old patent clerk in Bern, Switzerland, who published a paper that would destroy the Newtonian universe and replace it with something far more bizarre. Einstein made a simple but radical proposal. What if the speed of light is the same for everyone, no matter how fast they're moving? What if the speed of light is a universal constant built into the fabric of the universe itself? This sounds innocent enough until you really think through the implications. Imagine you're on a train moving at 60 miles per hour, and you throw a ball forward at 20 miles per hour relative to the train. Someone standing on the platform watching the train pass would measure the ball moving at 80 miles per hour, the sum of the train's speed and the ball's speed relative to the train. This is common sense. This is how velocities add up in everyday experience. But Einstein said light doesn't work that way. If you're on a train moving at half the speed of light and you shine a flashlight forward, Someone standing still would not measure the light moving at 1.5 times the speed of light. They would measure it moving at exactly the speed of light. The same speed you measure from the train. The same speed everyone measures, always, no matter what. This seems impossible. How can this be true? The only way this can work is if space and time themselves are not absolute. If moving clocks run slower and moving objects contract in length in just the right way to make the speed of light constant for everyone. This is special relativity, and it has been confirmed by thousands of experiments over the past century. Particles in accelerators live longer than they should because time slows down for them at high speeds. GPS satellites have to account for time dilation, or they give you completely wrong positions. Muons created in the upper atmosphere by cosmic rays shouldn't reach the ground before decaying, but they do because from their perspective, the atmosphere is contracted, and from our perspective, their internal clocks are running slow. Once you accept that the speed of light is constant, you have to accept something even stranger. Nothing can travel faster than light. Not objects, not signals, not information. The speed of light isn't just the speed of light. It's the speed of causality. It's the maximum speed at which cause can propagate to effect in our universe. And this brings us back to gravity. If nothing can travel faster than light, if the universe has a speed limit built into its very structure, then gravity can't be instantaneous. It has to propagate at some finite speed. And according to special relativity, that speed should be the speed of light. But this creates the paradox I mentioned at the beginning. If Earth responds to the sun's gravitational pull from 8 minutes in the past, why doesn't our orbit decay? Why is the solar system stable? The answer requires us to completely reimagine what gravity is. And that's where things get truly mind-bending. Let me ask you a provocative question that's going to seem completely unrelated at first, but I promise it will tie back to gravity in a way that will fundamentally change how you see the universe. Here it is. Are you moving right now? You're probably sitting down watching this video, so your instinct is to say no, you're not moving. But of course you are. Earth is rotating at about 1,000 miles per hour at the equator. Earth is orbiting the Sun at 67,000 miles per hour. The Sun is orbiting the center of the Milky Way at 514,000 miles per hour. The Milky Way is moving through space at 1.3 million miles per hour. So which is it? Are you moving or not? The answer, according to Newton, depends on your reference frame. Motion is relative. There's no absolute state of rest in the universe. You're at rest relative to your chair. You're moving relative to the sun. You're really moving relative to the center of the galaxy. All of these descriptions are equally valid. But Einstein realized something Newton missed. If motion is relative, and if the laws of physics are the same in all reference frames, that includes the speed of light. And if the speed of light is constant for everyone, then something very strange must be true about space and time themselves. Here's a thought experiment that illustrates this perfectly. Imagine you're on a train, and exactly at the midpoint of a train car, you set off a flash of light. The light expands outward in all directions at the speed of light, and it reaches the front wall and back wall of the train car at exactly the same time. This makes sense. The light travels equal distances to reach both walls, and it travels at the same speed in both directions, so it reaches both walls simultaneously. Now imagine I'm standing on the platform, watching this train go by. From my perspective, what do I see? I see the light flash go off at the midpoint of the car. I see the light expand outward, but I also see the train moving forward. So from my perspective, the back wall of the train is moving toward the point where the light flashed, and the front wall is moving away from it. The light still travels at the same speed in both directions, because the speed of light is constant, but now the back wall meets the light before the front wall does. So from your perspective on the train, the light hits both walls simultaneously. From my perspective on the platform, The light hits the back wall first, then the front wall. We disagree about whether two events happened at the same time. Simultaneity is relative. Events that are simultaneous in one reference frame are not simultaneous in another reference frame. This is not a trick. This is not a matter of perception or light travel time. This is a fundamental feature of reality. There is no absolute universal now that spans the entire universe. Different observers moving relative to each other have different definitions of what now means. Your now is not the same as my now if we're moving relative to each other. Think about how radical this is. Everything you've ever experienced suggests that time is universal, that everyone everywhere experiences the same present moment simultaneously. But that's wrong. The present moment is different for every observer moving at different speeds. The universe doesn't have a single present moment. It has infinite present moments depending on your motion. And here's where it connects to gravity. If simultaneity is relative, if different observers disagree about what events happen at the same time, then the concept of instantaneous gravitational action makes no sense. Instantaneous means happening at the same time. But the same time as what? The same time for whom? If the sun disappeared, there's no universal instant when all planets would feel it simultaneously, because there's no universal instant at all. This is why Einstein knew, even before working out the mathematics, that Newton's theory of gravity had to be wrong. Not approximately wrong, fundamentally wrong. Gravity couldn't be an instantaneous force acting across space. It had to be something else entirely. So Einstein set himself an audacious goal: create a new theory of gravity that was consistent with special relativity. A theory where gravitational effects propagate at the speed of light, no faster. A theory where gravity respects the cosmic speed limit. It took him 10 years. 10 years of intense mathematical work, countless wrong turns, and moments of profound insight. The result, published in 1915, was general relativity, and it's not an exaggeration to say it's one of the greatest intellectual achievements in human history. Here's the core idea, and it's so simple and yet so profound that it will make you see the world differently. Ready? Gravity is not a force. Gravity is the shape of spacetime. Let me explain with an analogy. Think of spacetime as a stretched rubber sheet. Now place a heavy ball on that sheet. The ball creates a dip, a curve in the sheet. Now roll a smaller ball across the sheet. As it approaches the heavy ball, it doesn't move in a straight line anymore. It curves toward the heavy ball, following the curved surface of the sheet. From the small ball's perspective, it feels like it's being pulled by a force. But really, it's just following the straightest possible path through curved space. This is what mass does to spacetime. The sun doesn't pull on Earth with a force. The sun curves spacetime around it, and Earth moves through that curved spacetime, following what's called a geodesic, the straightest possible path through curved space. Just like an airplane flying the shortest route from New York to Tokyo follows a curved path on Earth's surface, because Earth is curved. Planets follow curved paths through space because massive objects curve the space around them. Now here's the key insight that resolves our paradox. When the sun moves, it creates ripples in the curvature of spacetime. These ripples propagate outward at the speed of light. They're called gravitational waves, and they were first directly detected in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory, 100 years after Einstein predicted them. So gravity does travel at the speed of light after all. But, and this is crucial, the static gravitational field, the background curvature of spacetime, created by a massive object just sitting there, doesn't need to travel anywhere. It's already everywhere. It's the shape of space itself. Here's a better analogy. Imagine you're holding one end of a long rope, and your friend is holding the other end far away. The rope is taut between you. If you suddenly let go of your end, does your friend immediately feel it? No. A wave travels down the rope at a finite speed. determined by the rope's properties. And only when that wave reaches your friend does the tension release. But what if you shake your end of the rope side to side? Again, a wave travels down the rope. Your friend doesn't feel the shaking until the wave reaches them. Now here's the key question. While the rope is just hanging there, taut and unmoving, does the tension in the rope travel? No, the tension just is. It's a property of the rope's configuration. But changes in that tension, disturbances in that tension, those do travel. Space-time curvature works the same way. The sun creates a permanent curvature in space-time. That curvature just is. It doesn't travel. But if the sun suddenly moved, the information about that movement would propagate outward as gravitational waves at the speed of light. So if the sun vanished right now, Earth would continue orbiting the curved spacetime that exists here now for 8 minutes. Then the information about the sun's disappearance would arrive as gravitational waves. The curvature would flatten out, and Earth would be flung into space. But here's what's still bothering you, and rightfully so. The sun isn't sitting still. It's moving. It's orbiting the center of the galaxy. It's wobbling slightly due to Jupiter's gravitational influence. So shouldn't Earth be responding to where the sun was 8 minutes ago, causing orbital decay? This is where Einstein's theory reveals something so subtle and beautiful, it makes you appreciate the elegance of the universe. The answer is that Earth doesn't orbit where the sun is now, and it doesn't orbit where the sun was 8 minutes ago. It orbits where the sun is predicted to be based on the local curvature of spacetime here and now. Let me explain that more carefully, because this is the most mind-blowing part of general relativity. What if I told you that Earth isn't responding to the sun at all? That there's no signal traveling from the sun to Earth, telling Earth how to move? That Earth is just doing what objects do in curved spacetime, following the straightest possible path? This is the radical shift in thinking that general relativity requires. In Newton's theory, gravity is a force. Forces cause objects to accelerate, to change their motion. The sun exerts a force on Earth, pulling it toward the sun. Earth responds to this force by accelerating inward, which keeps it in orbit instead of flying off in a straight line. But in Einstein's theory, gravity isn't a force at all. Earth isn't being pulled. Earth is in free fall, floating freely through spacetime, experiencing no forces. From Earth's own perspective, it's moving in a perfectly straight line. It's just that spacetime itself is curved by the sun's presence. So a straight line through curved spacetime looks like a curved path to us. Think of it like this. Imagine you're flying from Los Angeles to Moscow. The shortest route, the most fuel-efficient route, is a great circle route that arcs up over the North Pole region. On a flat map, this looks curved. But on a globe, on the actual curved surface of Earth, this is the straightest possible path. You're not curving your trajectory. You're going straight. It's just that straight on a curved surface looks curved from a higher dimensional perspective. Earth is doing the same thing. Earth is going straight through spacetime. But because spacetime is curved by the sun's mass, straight looks like an ellipse to us, watching from a higher dimensional perspective. Now, if Earth is just following the local curvature of spacetime right here where it is, it doesn't need to know where the sun is now. It doesn't need to receive signals from the sun. It just needs to respond to the local geometry of spacetime at its location. And here's the beautiful part, that local geometry encodes information not just about where the sun is, but about where the sun is moving and how fast. The curvature of spacetime at Earth's location points not toward where the sun was 8 minutes ago, but toward where the sun will be when the effect of Earth's current motion propagates to the sun 8 minutes from now. This is called velocity-dependent terms in the gravitational field, and they're automatically built into Einstein's equations. The math is complex, but the idea is simple. The shape of spacetime at any point depends not just on the positions of massive objects, but on their velocities too. And it depends on these things in just the right way to eliminate the aberration problem that bothered Laplace. Let me give you an analogy that captures this. Imagine you're playing a video game and your character is moving around in a 3D environment. The environment has hills and valleys. Your character doesn't choose to move in curved paths. The game engine calculates the straightest path forward based on the local terrain at your character's current position and current velocity. As your character moves forward, the local terrain determines the next step, which determines the next step, and so on. Your character never needs to know about distant parts of the terrain. Everything is local. Spacetime works the same way. Every object moves based on the local curvature at its location and the direction it's already moving. The curvature here and now determines the next moment's motion, which determines the next moment's motion, and so on. No signals need to propagate. No information about distant objects needs to arrive. Everything is local. This is why the speed at which gravity propagates becomes almost irrelevant for objects in stable orbits. The stable curvature of spacetime is already there. It's not traveling. Only changes in that curvature propagate at the speed of light. But what about those changes? What happens when masses accelerate rapidly? What happens in violent cosmic events like neutron stars colliding or black holes merging? This is where gravitational waves come in. And this is where we can actually test whether gravity travels at the speed of light. On September 14, 2015, at 9 hours 50 minutes and 45 seconds UTC, both detectors of LIGO simultaneously registered a signal. It lasted only a fraction of a second, but it was unmistakable. Two black holes, 1.3 billion light-years away, had spiraled into each other and merged, releasing more energy in a fraction of a second than all the stars in the observable universe combined. But they didn't release this energy as light or heat. They released it as ripples in spacetime itself, gravitational waves. These waves traveled across the universe for 1.3 billion years, spreading out, diminishing in strength, until they finally reached Earth and passed through the LIGO detectors, stretching and squeezing spacetime by less than 1/10,000th the diameter of a proton. This was the first direct detection of gravitational waves, confirming a prediction Einstein made a century earlier. And it proved something crucial. Gravitational waves travel at the speed of light. How do we know? On August 17, 2017, LIGO detected gravitational waves from two neutron stars colliding. Not black holes this time, but neutron stars, which also emit light. And 1.7 seconds after the gravitational wave signal, gamma-ray telescopes detected a burst of light from the same event. The signals traveled 130 million light-years and arrived within 1.7 seconds of each other. This is remarkable. The gravitational waves and the light waves traveled for 130 million years and arrived within 2 seconds of each other. That means they were traveling at the same speed to within 1 part in a quadrillion. Gravity travels at the speed of light, not faster, not slower. Exactly the speed of light, to the limits of our measurement precision. But wait, you might be thinking, if the gravitational wave signal arrived first, even by just 1.7 seconds, doesn't that mean gravity traveled faster than light? No, and here's why. The gravitational waves were emitted slightly before the light. The collision of two neutron stars is a complex, violent process. The gravitational waves are emitted as the stars spiral inward. The light is emitted slightly later, after the collision has created a hot, glowing fireball of nuclear material. So the fact that we detected gravitational waves first doesn't mean they traveled faster. It means they left first. The universe has a speed limit, and gravity respects it. This is now confirmed. Gravity propagates at the speed of light. Einstein was right. But if Einstein was right, why does the solar system work? Why don't planets spiral into the sun due to aberration? We've talked about velocity-dependent terms in the gravitational field, but let's get more specific about what this actually means. and why it solves the problem so perfectly. Here's what will blow your mind. The reason Earth's orbit doesn't decay, the reason gravitational aberration doesn't destroy the solar system, is because gravity has something that Newton's theory completely missed: gravity-magnetic effects. And yes, I just said gravitomagnetic. Gravity has a magnetic component, just like electromagnetism has electric and magnetic components, and this changes everything. Let me explain by starting with electromagnetism, because it provides a perfect analogy and also reveals a deep connection between gravity and electromagnetism that Einstein spent the last 30 years of his life trying to understand. In the 1860s, James Clerk Maxwell unified the theories of electricity and magnetism into a single framework: electromagnetism. Before Maxwell, electricity and magnetism were thought to be separate phenomena. Electric charges create electric fields. Moving charges create magnetic fields. Static charges attract or repel each other via electric forces. Moving charges experience magnetic forces in addition to electric forces. Maxwell realized these weren't separate phenomena. They were different aspects of the same underlying field, the electromagnetic field, and he discovered something remarkable in the mathematics. Changes in the electromagnetic field propagate as waves at a specific speed determined by the properties of space itself. When Maxwell calculated this speed, he got 299,792,458 meters per second, the speed of light. This wasn't a coincidence. Light is electromagnetic waves. Maxwell had unified optics, electricity, and magnetism into a single theory. Now here's the key insight. In electromagnetism, a moving charge creates a magnetic field in addition to an electric field. And this magnetic field does something crucial. It creates a force on other moving charges that partially cancels the electric force in just the right way to eliminate aberration. What does that mean? Imagine you have two charged particles moving parallel to each other at the same speed. Each particle creates an electric field that pushes on the other particle. But because they're moving, each particle also creates a magnetic field, and the magnetic force between moving charges partially cancels the electric force. The faster they move, the stronger the magnetic cancellation. At the speed of light, the cancellation would be complete. This means that when you account for both electric and magnetic effects, charged particles interact based on where they appear to be when you account for their motion and the finite speed of electromagnetic propagation, not based on where they were when the signal left. General relativity has the exact same structure, but for gravity instead of electromagnetism. A stationary mass creates a gravitational field analogous to an electric field, but a moving mass creates a gravitomagnetic field analogous to a magnetic field. And this gravitomagnetic field creates additional effects on other moving masses that partially cancel the normal gravitational effects in just the right way to eliminate aberration. This is not obvious in the mathematics. Einstein's field equations are complex, nonlinear, and difficult to solve exactly. But when you work out the approximate solutions for slowly moving objects in weak gravitational fields, which includes everything in the solar system, you find these velocity-dependent terms, these gravitomagnetic effects. The mathematician and physicist Oliver Heaviside first explored this analogy between gravity and electromagnetism in the 1890s, before Einstein developed general relativity. Heaviside took Newton's law of gravity and asked, what if gravity propagates at a finite speed like electromagnetism? What additional terms would appear in the equations? And he found that if you add velocity-dependent terms analogous to the magnetic terms in electromagnetism, the aberration problem goes away. Einstein's general relativity, developed from completely different principles, produces exactly these terms. And they've been tested. Gravitomagnetic effects are real, they've been measured, and they're exactly what Einstein's theory predicts. One of the most dramatic confirmations came from an experiment called Gravity Probe B. So let me bring this all together. Does gravity travel faster than the speed of light? No. Gravitational waves, changes in the gravitational field, propagate exactly at the speed of light. This has been confirmed by direct observation. But does that mean planets orbit where the sun was 8 minutes ago? Also no. Planets orbit based on the local curvature of spacetime at their current position. That curvature encodes information about the sun's position and velocity in a way that automatically accounts for the finite speed of gravity propagation through velocity-dependent gravitomagnetic terms. The solar system is stable because Einstein's equations are self-consistent. The mathematics works out perfectly so that objects in stable orbits don't experience aberration effects. It's not that gravitational aberration is small. It's that it's exactly canceled by gravitomagnetic effects. This is one of those moments where the elegance of physics makes you appreciate the universe. The laws of nature aren't just accurate. They're beautiful. They're mathematically consistent in ways that aren't obvious until you dig deep into the theory. But we're not done. Because there's another question lurking beneath all of this, a question that physicists still don't have a complete answer to. If gravity is the curvature of spacetime, what is spacetime? What is it made of? And how does curvature in one region of spacetime propagate to another region at the speed of light? To answer that, we need to go even deeper into the nature of reality itself. Think of the universe as an ocean. Not a metaphor, but an actual ocean filling all of space. In this ocean, particles are not fundamental objects. They're waves, ripples, excitations of underlying fields that permeate all of space. This is quantum field theory, the most accurate scientific theory we have. It describes particles as excitations of quantum fields. An electron isn't a little ball. It's a wave in the electron field. A photon isn't a particle of light. It's a wave in the electromagnetic field. Every fundamental particle is a wave in its corresponding quantum field. And gravity? If quantum field theory is correct, and if gravity can be described quantum mechanically, then gravitational waves should also be quantized. They should be made of particles called gravitons, just like electromagnetic waves are made of photons. But here's where we run into a profound problem. Nobody has ever detected a graviton. More than that, it might be impossible to detect a graviton, even in principle, because gravitational interactions are so weak. Let me give you a sense of scale. The electromagnetic force between two protons is about 10 to the 36th power stronger than the gravitational force between them. That's 1 followed by 36 zeros. Gravity is absurdly weak compared to the other forces of nature. This is called the hierarchy problem, and nobody fully understands why gravity is so much weaker. Because gravity is so weak, individual gravitons carry incredibly tiny amounts of energy. Detecting a single graviton would require a detector so massive and so sensitive that it would collapse into a black hole under its own gravity. This isn't a limitation of our technology. This is a fundamental limit imposed by the laws of physics as we currently understand them. So we have this strange situation where theory predicts gravitons should exist, but we can't detect them and probably never will. Does that mean they don't exist? Or does it mean our theory is wrong? Or does it mean something deeper about the nature of reality? Here's where it gets really philosophical. In quantum field theory, we never actually observe fields directly. We observe particles. We detect electrons, photons, quarks. The fields are mathematical abstractions, useful for making predictions but not directly observable. We infer the existence of fields because particle behavior makes sense when we think of particles as field excitations. But with gravity, we observe space-time curvature directly. We observe the paths of planets and light bending around massive objects. We observe time dilation near massive objects. We observe gravitational waves stretching and squeezing space. we directly experience the effects of spacetime geometry. So which is more fundamental? Is spacetime curvature an emergent phenomenon that arises from the quantum behavior of gravitons, just like ocean waves arise from the collective motion of water molecules? Or are gravitons a mathematical convenience, a way of quantizing spacetime curvature that doesn't reflect any underlying reality? Physicists have been grappling with this question for nearly a century, and we still don't have a definitive answer. The problem is that general relativity and quantum field theory, our two most successful theories, seem to be fundamentally incompatible. General relativity is a classical theory. It treats spacetime as a smooth, continuous fabric that can be curved and warped by matter and energy. Quantum field theory is, well, quantum. It treats everything as discrete, probabilistic, subject to Heisenberg's uncertainty principle. Particles don't have definite positions and velocities simultaneously. Fields undergo quantum fluctuations. The vacuum isn't empty. It's seething with virtual particles, constantly popping in and out of existence. When you try to apply quantum principles to gravity, the mathematics breaks down. Calculations give infinite answers that can't be removed by standard mathematical techniques. The theory is non-renormalizable, meaning it can't make predictions at very high energies or very short distances. This suggests that general relativity, despite its incredible success at predicting the behavior of planets, stars, and even black holes, is not the final theory of gravity. It's an approximation, valid at large scales and low energies, but breaking down at the smallest scales where quantum effects become important. The scale where quantum effects become important for gravity is called the Planck scale, named after Max Planck, the physicist who first introduced the concept of quantization in 1900. The Planck length is about 10 to the minus 35 meters. That's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000. To give you a sense of how small this is, the Planck length is to an atom what an atom is to the solar system. At the Planck scale, quantum fluctuations in spacetime itself become significant. Spacetime stops being a smooth fabric and becomes foamy, chaotic, with quantum fluctuations creating and destroying microscopic black holes, wormholes, and who knows what else. This is called quantum foam, or spacetime foam, and it represents the limits of our current understanding. Nobody knows what physics looks like at the Planck scale. General relativity predicts smooth spacetime. Quantum mechanics predicts violent fluctuations. We need a theory of quantum gravity that unifies these two perspectives, and we don't have one yet. There are candidates. String theory proposes that fundamental particles aren't point-like objects, but tiny vibrating strings, and that spacetime itself has extra dimensions beyond the 3 of space and 1 of time that we experience. Loop quantum gravity proposes that spacetime itself is quantized, made of discrete chunks called spin networks. Other approaches include causal dynamical triangulations, asymptotic safety, and emergent gravity theories. But none of these theories have been experimentally confirmed, because we can't probe the Planck scale with current technology. We'd need a particle accelerator the size of the galaxy to reach the energies where quantum gravitational effects become measurable. We're stuck theorizing without direct experimental guidance. However, and this is fascinating, we might be able to test quantum gravity indirectly by looking at the early universe. In the first fraction of a second after the Big Bang, the entire observable universe was compressed to a size smaller than an atom. At those energies and densities, quantum gravitational effects were important, and those effects might have left imprints in the cosmic microwave background radiation, the afterglow of the Big Bang that we can still detect today. Physicists are searching for specific patterns in the cosmic microwave background that would indicate quantum gravitational effects during inflation, the period of exponential expansion in the first fraction of a second after the Big Bang. If we find these patterns, we'll have our first experimental evidence for quantum gravity. If we don't, we'll have ruled out entire classes of quantum gravity theories. But here's what I want you to appreciate. The question, does gravity travel faster than light? Led us on a journey from Newton's instantaneous action at a distance, through Einstein's curved spacetime, to gravitational waves propagating at the speed of light, to gravitomagnetism and frame dragging, and finally to the quantum nature of spacetime itself. And at every step, we have discovered that reality is stranger, more subtle, more interconnected than we imagined. The speed at which gravity propagates isn't just a technical detail. It's intimately connected to the structure of spacetime, the nature of causality, the relationship between quantum mechanics and gravity, and ultimately the origin and fate of the universe itself. And we're still not done, because there's an even deeper question. If gravitational waves carry energy, and energy curves spacetime according to Einstein's equations, do gravitational waves gravitate? Do they create their own gravitational fields? And if so, what does that mean for how gravity propagates? What if I told you that gravitational waves have gravity, that they curve spacetime themselves, creating additional gravitational effects? This sounds like it should create a feedback loop. Gravitational waves generating more gravitational waves, generating more gravitational waves, spiraling out of control. But the mathematics of general relativity handles this beautifully through the nonlinearity of Einstein's equations. Let me explain what nonlinear means in this context. In Newton's theory of gravity, if you have two masses, each creates its own gravitational field, and the total gravitational field is just the sum of the two individual fields. This is called the principle of superposition, and it's a feature of linear theories. You can calculate the effect of each source independently and add them up. But Einstein's equations are nonlinear. Spacetime curvature itself carries energy, and energy curves spacetime, so the gravitational field interacts with itself. You can't just calculate the effect of each mass independently and add them up. The total curvature is more than the sum of the parts, because the curvature itself contributes to the curvature. This makes Einstein's equations fiendishly difficult to solve. For most situations, physicists have to use approximations or numerical simulations on supercomputers. But this nonlinearity is also what makes general relativity so rich and interesting. It leads to phenomena that have no analog in Newtonian gravity. For example, gravitational waves can interact with other gravitational waves. Two gravitational waves colliding can scatter off each other, even though they're just ripples in spacetime with no mass. This is predicted by Einstein's equations and has been calculated in detail, though it's so weak it's probably impossible to observe directly. More dramatically, if gravitational waves become strong enough, they can focus and amplify themselves through nonlinear effects. In the most extreme cases, this could theoretically create what's called a black hole bomb or a gravitational wave collapse, where intense gravitational waves implode under their own gravity and form a black hole. This has never been observed, and it probably requires energies far beyond anything in the current universe. But it might have happened in the early universe, in the first moments after the Big Bang, when energies were extreme. Some theories propose that primordial black holes formed in the early universe, rather than from collapsing stars, could have been created by gravitational wave collapse. The nonlinearity of general relativity also has implications for how gravitational waves propagate. In a perfectly flat, empty spacetime, gravitational waves propagate at exactly the speed of light without changing shape. But in a curved spacetime, gravitational waves can be bent, focused, or scattered by the background curvature, just like light can be bent by gravitational lensing. This means that gravitational waves from distant sources can take multiple paths to reach us, arriving at different times, just like light from gravitationally lensed quasars. This hasn't been observed yet, but as gravitational wave astronomy becomes more sensitive, we should start detecting these effects. There's another subtle effect worth mentioning. Gravitational waves carry energy away from the system that emits them. Two black holes spiraling toward each other lose energy by emitting gravitational waves, and this energy loss causes them to spiral inward faster, which makes them emit stronger gravitational waves, which causes more energy loss, creating a runaway process that ends with the black holes merging. This is called gravitational wave radiation reaction, and it's been tested to incredible precision. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar system, two neutron stars orbiting each other with a period of about 8 hours. By precisely timing the radio pulses from one of the neutron stars, they could measure the orbital period with extraordinary accuracy. Einstein's theory predicts that this system should be losing energy to gravitational waves, causing the orbital period to decrease by about 76 millionths of a second per year. Hulse and Taylor monitored the system for years, and the orbital decay matched Einstein's prediction to within a fraction of a percent. This was the first indirect evidence for gravitational waves, and Hulse and Taylor won the Nobel Prize in Physics in 1993 for this discovery. Think about what this means. Two neutron stars, 21,000 light-years away, each with the mass of the Sun compressed into a sphere 20 kilometers across, orbiting each other at a significant fraction of the speed of light, are losing energy to ripples in spacetime itself. And we can measure this energy loss by timing radio pulses with nanosecond precision. This is one of those moments where physics feels almost magical. We can't see these neutron stars directly. We can't send a probe there. We can't even detect the gravitational waves they're emitting, which are too weak by the time they reach Earth. But we can infer their entire orbital evolution from radio pulse timing and confirm Einstein's century-old prediction to astonishing precision. The Hulse-Taylor pulsar is now spiraling inward due to gravitational wave emission. In about 300 million years, the two neutron stars will merge in a cataclysmic event that will release more energy in gravitational waves than all the stars in the observable universe emit in light. The gravitational waves from that merger will wash over Earth, assuming we're still around to detect them, and they'll tell us the final moments of this billion-year cosmic dance. But let's bring this back to our original question. Does gravity travel faster than light? We've established that gravitational waves travel at the speed of light. But there's a subtlety here that's worth exploring. What we mean, this is a deep insight. Space and time aren't separate entities that happen to be connected by a speed limit. They're aspects of a unified structure called spacetime, and the speed of light is just the exchange rate between the space part and the time part. When we ask whether gravity travels faster than light, we're really asking whether gravitational effects can propagate faster than causality allows. And the answer is definitively no. The universe has a causal structure. Events can only influence other events within their future light cone, the region of space-time that can be reached at or below the speed of light. Gravitational effects respect this causal structure. This has profound implications for the nature of reality. It means the universe is local. What happens here depends only on conditions in the immediate vicinity, not on distant events that haven't had time to influence us yet. It means we're protected from causal paradoxes, situations where effects precede their causes. It means the universe makes sense, at least in this respect. But quantum mechanics throws a wrench into this tidy picture, and this is where things get truly weird. Here's a question that's going to make you uncomfortable. If nothing can travel faster than light, if the universe respects locality and causality, how do you explain quantum entanglement? Quantum entanglement is a phenomenon where two particles can be correlated in ways that seem to require faster-than-light communication. Einstein famously called it spooky action at a distance, and he thought it proved that quantum mechanics was incomplete that there must be hidden variables we don't know about? Let me give you a concrete example. Imagine you create two photons in a special way so that their polarizations are entangled. You send one photon to Alice on Earth and one photon to Bob on Mars. The photons are now separated by light minutes of distance. Alice measures the polarization of her photon and finds it's vertical. At that instant, before any signal could possibly reach Bob, Bob's photon collapses into horizontal polarization. This seems to violate everything we've said about causality and the speed of light. How does Bob's photon know that Alice measured her photon? How does the information travel from Earth to Mars instantaneously? The resolution to this paradox is subtle and has been the subject of intense debate for decades. The key insight is that while quantum entanglement creates correlations that appear non-local, it cannot be used to transmit information faster than light. Here's why. Before Alice measures her photon, she can't predict what results she'll get. The outcome's fundamentally random. She has a 50% chance of measuring vertical and a 50% chance of measuring horizontal. When she measures vertical, Bob's photon becomes horizontal, but Bob doesn't know this until Alice sends him a classical message, traveling at or below the speed of light, telling him what she measured. From Bob's perspective, his photon is in a mixed state until Alice tells him her measurement result. He measures random polarizations, 50% vertical and 50% horizontal, showing no pattern. Only when he compares his results with Alice's results does he see the correlation. And to compare results, they need to communicate classically. So quantum entanglement doesn't allow faster-than-light communication. It creates correlations, but you can't use those correlations to send information. Causality is preserved. But here's what's deeply strange. Those correlations are real. They've been tested in countless experiments, and they violate what are called Bell inequalities, mathematical constraints that any theory with local hidden variables must satisfy. Quantum mechanics violates these constraints, and experiments confirm that nature violates them too. This means the universe is either non-local, with instantaneous connections across space, or non-real, meaning particles don't have definite properties until they're measured, or both. These are the only options consistent with experimental results, and they're all deeply uncomfortable. What does this have to do with gravity? Well, if space-time itself is fundamentally quantum, if there's such a thing as quantum superposition of space-time geometries, then we might be able to create entangled spacetimes. And this gets weird fast. Some theoretical physicists have proposed that quantum entanglement and space-time geometry are intimately connected through something called E equals EPR correspondence. ER stands for Einstein-Rosen bridges, also known as wormholes, hypothetical tunnels through space-time, connecting distant regions. EPR stands for Einstein-Podolsky-Rosen, the paper where Einstein and colleagues first described quantum entanglement. The E equals EPR conjecture, proposed by Leonard Susskind and Juan Maldacena in 2013, suggests that entangled particles are connected by microscopic wormholes. The entanglement doesn't involve faster-than-light communication because the particles are connected through the geometry of space-time itself, not through three-dimensional space. This is speculative, cutting-edge theoretical physics that hasn't been experimentally confirmed. But if true, it suggests a deep connection between quantum mechanics and gravity. Space-time geometry might emerge from quantum entanglement. Space itself might not be fundamental, but rather an emergent phenomenon arising from the quantum entanglement structure of the universe. Mark van Raamsdonk and others have explored this idea through what's called the holographic principle, which suggests that the information content of a region of space is proportional to the area of its boundary, not its volume. This implies that our three-dimensional universe might be a holographic projection of information encoded on a two-dimensional boundary. If space-time is emergent, if it's not fundamental but arises from some deeper quantum structure, then the question, Does gravity travel faster than light? Might not even be well defined at the most fundamental level. Gravity, space-time, and the speed of light might all be emergent phenomena that only make sense at scales larger than the Planck scale. This is where modern physics is heading. We're starting to suspect that space-time is not the fundamental fabric of reality, but rather an approximation that emerges. At large scales, just like temperature and pressure, are emergent properties of molecular motion that don't exist for individual molecules. If this is true, then at the deepest level, there is no space-time, no gravity, no speed of light. There's just quantum information organized in ways we don't yet fully understand. And space-time geometry emerges from that organization when you average over vast numbers of quantum degrees of freedom. This would be a conceptual revolution even more profound than the shift from Newton to Einstein. It would mean that everything we think of as fundamental, space, time, matter, energy, is actually emergent. The universe at its core might be pure information, with the physical world we experience being a kind of shadow or projection of that information. But we're getting ahead of ourselves. These are ideas at the cutting edge of theoretical physics, still being developed, still being debated. They might be right, or they might be completely wrong. The point is that the question of how gravity propagates has led us to the deepest questions in physics. What is space-time? Is it fundamental or emergent? How do quantum mechanics and gravity fit together? What is the nature of reality at the most fundamental level? And we don't have complete answers yet, but we're working on it, and that's exciting. Let me bring this down to Earth for a moment and talk about how the speed of gravitational propagation affects you personally, because it does, every single day, in ways you probably never thought about. Your sense of weight, the feeling of gravity pulling you down, is actually you being accelerated upward by the ground beneath your feet. This sounds backwards, but it's correct from the perspective of general relativity. You're not being pulled down. You're trying to fall freely through curved spacetime, following a geodesic, but the ground is in your way, pushing you upward, accelerating you away from your natural geodesic motion. This is why you feel weightless in free fall. When you're falling, you're not fighting gravity. You're giving in to it completely, following your natural path through curved spacetime. Astronauts in orbit aren't in zero gravity. They're in free fall, continuously falling toward Earth, but also moving sideways fast enough that they keep missing. They feel weightless because they're following geodesics, moving naturally through curved spacetime without any forces acting on them. Now, the space-time curvature that you're responding to, that creates your weight, was generated by Earth's mass. But which Earth mass? The Earth as it is now, or as it was some tiny fraction of a second ago, when gravitational effects had time to propagate from Earth's center to the surface? The answer is it doesn't matter for all practical purposes, because Earth is not accelerating significantly. The static curvature is already there. But if Earth suddenly disappeared, you'd continue to feel gravity for about 0.001 seconds, the time it takes for the information about Earth's disappearance to propagate from Earth's center to the surface as gravitational waves. For 1 millisecond after Earth vanished, you'd still feel weight. Then suddenly, nothing. You'd be floating in space, still moving at whatever velocity you had when Earth disappeared, but no longer experiencing any gravitational force. This isn't just theoretical. Gravitational waves from distant cosmic events pass through Earth all the time. Right now, as you're reading this, gravitational waves from black hole mergers and neutron star collisions billions of light years away are passing through your body, stretching and squeezing spacetime by infinitesimal amounts. LIGO can detect these waves because it's incredibly sensitive, using lasers to measure changes in arm lengths of less than 1,000th the diameter of a proton. But your body experiences these waves too. You're being stretched and squeezed in rhythm with cosmic catastrophes happening billions of years ago. You just can't feel it because the effect is so small, and your body isn't a precise enough measuring instrument. But here's what's profound. Those gravitational waves encode information about the events that created them. When LIGO detects a signal, physicists can work backward and figure out the masses of the black holes that collided, how fast they were spinning, how far away they were, and even test whether Einstein's equations correctly predicted the waveform. Gravitational waves are a new way of observing the universe. For all of human history until 2015, we observed the cosmos through electromagnetic radiation, light, radio waves, X-rays, gamma rays. But electromagnetic waves are easily absorbed and scattered by matter. Gravitational waves pass through everything almost unimpeded. They carry information from regions of the universe that are opaque to light. This opens up entirely new ways of studying the cosmos. We can now observe black hole mergers directly. We can study neutron-star collisions and learn about the equation of state of nuclear matter at extreme densities. We might even detect gravitational waves from the Big Bang itself, from the first fraction of a second, when the universe was so hot and dense that it was opaque to electromagnetic radiation. The cosmic microwave background radiation, the afterglow of the Big Bang that we can see with radio telescopes, comes from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely. But gravitational waves from the Big Bang would come from much earlier, from the inflationary epoch, giving us a window into physics at energies we could never achieve in particle accelerators. If we detect primordial gravitational waves, it would confirm inflation, tell us the energy scale at which inflation occurred, and potentially give us evidence for quantum gravity. It would be one of the most important discoveries in the history of science. But even without detecting primordial gravitational waves, gravitational wave astronomy is revolutionizing our understanding of the universe. We're detecting events that were completely invisible before. We're testing general relativity in the strong field regime, where space-time curvature is extreme. We're opening a new window on the cosmos. And all of this is possible because gravity propagates at a finite speed, carrying information across the universe in the form of ripples in space-time itself. So when you ask, does gravity travel faster than light? The answer is no, but the implications of that answer are vast. It means the universe has a causal structure. It means information can't travel faster than light, even gravitational information. It means we can detect and study gravitational waves. It means space-time is a dynamical entity that can carry waves and transport energy. It means the universe makes sense in a deep, mathematical way. And it means we're living in a moment in history where we're learning to observe the universe in an entirely new way, opening doors that were closed for all of human history until just a few years ago. What if I told you that the speed of gravity might not be constant throughout the history of the universe? That in the early universe, or in exotic states of matter, the speed at which gravitational effects propagate might be different from the speed of light today? This is speculative, but it's based on some serious theoretical work. In some modified theories of gravity, theories that extend or modify Einstein's general relativity, the speed of gravitational waves can differ from the speed of light under certain conditions. Why would anyone want to modify general relativity? After all, it's been tested extensively and passed every test. The reason is that general relativity, as successful as it is, has some problems. It predicts its own breakdown at singularities inside black holes and at the Big Bang. It doesn't incorporate quantum mechanics. And it might not be able to explain some cosmological observations without adding exotic ingredients like dark matter and dark energy. Dark energy is particularly puzzling. Observations tell us the universe's expansion is accelerating. Distant galaxies are moving away from us faster and faster. This requires some form of energy that pervades all of space and pushes everything apart. We call it dark energy, but we don't know what it is. The simplest explanation is that space itself has energy, described by a cosmological constant in Einstein's equations. But when we try to calculate what this energy should be based on quantum field theory, we get an answer that's wrong by a factor of 10 to the 120th power. That's not just wrong. That's the worst prediction in the history of physics. Some physicists think this might be telling us that general relativity needs to be modified at very large scales. Maybe gravity doesn't quite follow Einstein's equations when you're looking at the entire universe. Maybe there are additional terms in the equations that only become important at cosmological distances. These modified gravity theories have names like FR gravity, scalar tensor theories, massive gravity, and many others. And in some of these theories, the speed of gravitational waves can differ from the speed of light. For example, in massive gravity theories, the graviton has a tiny but non-zero mass. This would cause gravitational waves to travel slightly slower than light, with the difference depending on the graviton mass and the frequency of the wave. The joint observation of gravitational waves and electromagnetic waves from the neutron-star collision in 2017 constrained this possibility severely, showing that if the graviton has mass, it's incredibly small. But we can't rule it out completely. In other modified theories, the speed of gravitational waves could vary with frequency or with the energy density of the environment they're traveling through. These are exotic possibilities, but they haven't been ruled out by observations yet. There's also the question of what happened in the very early universe during inflation. Inflation is the hypothesis that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. During inflation, the universe doubled in size every 10 to the minus 37 seconds or so, expanding faster than the speed of light. Wait, doesn't that violate what we said about nothing traveling faster than light? No, because the expansion of space itself isn't limited by the speed of light. Special relativity says objects can't move through space faster than light, but it doesn't constrain how fast space itself can expand. During inflation, objects at opposite sides of the universe were carried apart faster than light by the expansion of space itself. During this period, the behavior of spacetime was extreme. The energy density was enormous. Quantum effects were important, and the usual rules of general relativity might not have applied. Some theories of inflation predict that gravitational waves were produced during this era, and these primordial gravitational waves would carry information about the physics of inflation. If we detect these primordial gravitational waves, we might discover that the speed of gravitational propagation was different during inflation than it is today. This would be revolutionary, telling us that the fundamental constants of nature might not actually be constant, but could vary under extreme conditions. This is all speculative, but it's the kind of speculation that's grounded in serious theoretical work and could potentially be tested by future observations. We live in an exciting time where we have both the theoretical frameworks to make predictions and the observational technology to test them. But let's bring this back to something more concrete. Even in standard general relativity, without any modifications, there's a sense in which the speed of gravity can appear to vary depending on the observer. Remember when we talked about how the speed of light is constant for all observers? That's true locally, meaning if you measure the speed of light right next to you, you'll always get c. But if you're watching light travel past a massive object from far away, it appears to move slower because the light is climbing out of a gravitational potential and time is running slower near the massive object. This is called the Shapiro time delay, after Erwin Shapiro, who predicted it in 1964. When radar signals pass near the sun, they take longer to make the round trip than you'd expect from their distance and the speed of light, because spacetime is curved near the sun, and time runs slower in curved spacetime. The same effect applies to gravitational waves. If gravitational waves pass near a massive object on their way to us, they experience a time delay. From our perspective far away, it looks like the gravitational waves slowed down as they passed the massive object. This isn't really a change in the speed of gravitational waves. Locally, at any point along their path, the gravitational waves are traveling at speed c through spacetime. But globally, from the perspective of a distant observer, they appear to take a detour through curved spacetime that makes them arrive later than they would in flat spacetime. This is exactly analogous to light. Light always travels at speed c locally, but its path is curved by gravity, making it appear to slow down or take detours from a distant perspective. These subtle effects are measurable. Gravitational waves from distant sources should show arrival time delays if they pass near massive objects on the way to us. This is gravitational lensing of gravitational waves, and it's something we hope to observe in the future as gravitational wave detectors become more sensitive. In fact, just like we see multiple images of gravitationally lensed quasars, because light takes different paths around the lensing galaxy, we should be able to detect multiple copies of the same gravitational wave signal arriving at different times if the waves are lensed by intervening masses. This would give us a completely new way to study massive objects in the universe. We could use gravitational wave lensing to weigh galaxies and galaxy clusters, to map dark matter, and to study cosmology. It's an entirely new tool that we're just beginning to develop. So even though gravitational waves travel at the speed of light locally, their journey across the universe is shaped by spacetime curvature in ways that create observable effects. The speed of gravity isn't just a number. It's part of a rich structure connecting geometry, causality, and the evolution of the universe. Let me tell you about one of the most mind-bending implications of gravity propagating at the speed of light. It has to do with black holes, and it's going to challenge everything you think you understand about cause and effect. Imagine you're watching a star collapse into a black hole from a safe distance. The star runs out of fuel, can't support itself against gravity, and collapses. In Newtonian physics, the moment the star collapses past a certain size, it becomes a black hole, and that's that. But in general relativity, things are much stranger. From your perspective watching from far away, the collapse appears to slow down as the star approaches its Schwarzschild radius, the size at which it becomes a black hole. The light from the star's surface gets more and more redshifted, and time appears to run slower and slower on the star's surface. In fact, from your perspective, the star never quite finishes collapsing. It takes infinite time to reach the event horizon, but from the perspective of someone falling into the black hole with the collapsing star, nothing special happens at the event horizon. They pass through it in finite time, experiencing no infinite delays. They're doomed. They'll hit the singularity at the center in short order, but the event horizon crossing is uneventful. This is called the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. The issue is this: quantum mechanics says information can't be destroyed. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any other time. Information is conserved. But black holes seem to destroy information. If you throw a book into a black hole, the information encoded in that book crosses the event horizon and falls into the singularity. From the outside, it's gone forever. The black hole just gets slightly more massive. It doesn't matter whether you threw in a book, a computer, or a star. All that matters is the mass, charge, and angular momentum of what fell in. Everything else, all the detailed information, is lost. Stephen Hawking made this problem even worse in 1974 when he discovered that black holes aren't completely black. They emit thermal radiation due to quantum effects near the event horizon, now called Hawking radiation. Over incredibly long timescales, black holes evaporate, slowly losing mass until they disappear completely. When the black hole finally evaporates, what happens to the information that fell in? Hawking initially thought it was destroyed, violating the principles of quantum mechanics. This led to a fierce debate that lasted for decades. The resolution, which is still being worked out, involves understanding that information can be encoded in correlations between the Hawking radiation particles emitted at different times. The information isn't destroyed. It's scrambled into the Hawking radiation in subtle, highly non-local ways that take the entire evaporation time to fully emerge. But here's where the speed of gravity becomes crucial. Hawking radiation is created by quantum effects in curved spacetime. Virtual particle pairs are constantly being created near the event horizon. Normally, these pairs annihilate each other almost immediately. But near an event horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real Hawking radiation. The rate at which this happens depends on the curvature of spacetime near the event horizon, which depends on the mass and spin of the black hole, which depends on everything that's ever fallen into it. So the Hawking radiation being emitted now encodes information about matter that fell in earlier. But how does the information about matter that crossed the event horizon get encoded in radiation that's emitted outside the horizon? The event horizon is supposed to be a one-way boundary. Information can't escape from inside. The answer involves understanding that the event horizon isn't a local feature. It's a global feature that depends on the entire future evolution of spacetime. From a local perspective at the horizon, there's nothing special. Spacetime is smooth, and particles cross it without noticing. But from a global perspective, the horizon represents a boundary beyond which events can't influence the external universe. The information doesn't travel back out through the horizon. Instead, it gets encoded in subtle correlations in the quantum state of the radiation field that straddles the horizon. These correlations are non-local, spread across regions that are space-like separated, meaning they're far enough apart that light can't travel between them in the available time. This is where quantum entanglement comes back in. The Hawking radiation isn't just thermal noise. It's maximally entangled with the interior of the black hole. As the black hole evaporates, the entanglement structure evolves in precisely the right way to preserve information. But you need to collect all the radiation over the entire evaporation time to reconstruct the information about what fell in. And here's the really deep point. The fact that gravity propagates at the speed of light, no faster, is crucial for this to work. If gravitational effects could propagate faster than light, the causal structure of spacetime would be different, and the careful accounting of information in black hole evaporation would break down. The speed of gravity is intimately tied to the preservation of information in quantum mechanics, to the resolution of the black hole information paradox, and ultimately to whether the universe is fundamentally predictable, or whether information can truly be destroyed. This might seem abstract, but it has profound implications. If information can be destroyed, then the universe isn't deterministic. Identical initial conditions could lead to different outcomes. The laws of physics would be fundamentally probabilistic in a way that goes beyond quantum mechanics. Everything we think we understand about cause and effect would need to be revised. The fact that gravity respects the cosmic speed limit helps preserve the deterministic structure of quantum mechanics, even in the presence of black holes. It's another example of how the speed of gravitational propagation isn't just a technical detail. It's deeply connected to the fundamental nature of reality. All right, let's talk about something that's going to make you question everything we've discussed so far. What if I told you that in some sense, gravity doesn't propagate at all? That the entire concept of gravitational waves traveling from one place to another is a convenient fiction, and what's really happening is something far stranger. This is the perspective from what's called the ADM formalism of general relativity, developed by Richard Arnowit, Stanley Deser, and Charles Misner in the 1960s. In this formalism, you split space-time into space and time explicitly, and you think of general relativity as describing how the geometry of space evolves over time. From this perspective, the universe at any instant is a three-dimensional space with a certain geometry. As time advances, this geometry changes. Matter and energy sources create curvature in the three-dimensional space, and this curvature evolves according to Einstein's equations. But here's the weird part. In the ADM formalism, there's no absolute notion of now across space. Different choices of how to slice space-time into moments of space and moments of time are equally valid. This is called the choice of foliation, and it's arbitrary. Different foliations give you different descriptions of the same physical reality. When you make one choice of foliation, you might see gravitational waves propagating across space at the speed of light. When you make a different choice, those same waves might appear to propagate instantaneously, or not propagate at all. The choice of foliation changes what counts as propagation versus what counts as already there. This sounds crazy, but it's a consequence of the fact that space-time is a four-dimensional structure, and splitting it into space plus time is arbitrary. It's like looking at a solid object from different angles. The object doesn't change, but your view of it does. So in what sense do gravitational waves really propagate? The answer is that propagation is a coordinate-dependent concept. What's coordinate-independent, what everyone agrees on, is the space-time geometry itself. Whether you describe the geometry as waves propagating through space or as space evolving in time is a matter of perspective. This is deeply unsettling for most people because we're used to thinking of propagation as an objective physical process. A sound wave propagates through air. We can see the air molecules moving. An electromagnetic wave propagates through space. We can detect it with antennas. But gravitational waves are ripples in space-time itself, and whether they're propagating or just there in the geometry depends on your choice of coordinates. Let me give you an analogy that might help. Imagine you're looking at the ocean. You see waves moving across the surface. The waves are clearly propagating from one place to another. But now imagine you're in a submarine underwater and you're feeling the pressure variations as waves pass overhead. From your perspective, you're not seeing waves propagate horizontally. You're experiencing a time-varying pressure at a fixed location. Both descriptions are valid. The waves are propagating horizontally across the surface, and they're also creating time-varying conditions at fixed underwater locations. Which description you use depends on your perspective and what you're measuring. Gravitational waves are similar. From one perspective, they're ripples in space-time propagating outward at the speed of light. From another perspective, they're time-varying geometries at different locations in space. Both descriptions capture the same physical reality. But there's an important difference between these perspectives. Some choices of coordinates, some ways of describing the geometry, are more useful than others. The description where gravitational waves propagate at the speed of light is useful because it makes the causal structure of space-time manifest. It makes it clear what events can influence what other events. If you choose coordinates where gravitational effects appear to propagate instantaneously, you're hiding the causal structure of space-time. You're making it look like distant events can influence each other without delay. But this is an artifact of your coordinate choice, not a physical reality. This is analogous to how you can use coordinates on Earth, where the North Pole appears to be infinitely far away, like the standard latitude-longitude coordinates, but that doesn't mean the North Pole is actually infinitely far away. It's a coordinate singularity, an artifact of your choice of coordinates. So while it's true that the propagation of gravity is coordinate dependent, the physically meaningful statement is that space-time has a causal structure, and this causal structure is respected by gravitational effects. No matter what coordinates you choose, you can't use gravitational effects to send information faster than light. You can't create causal paradoxes. The speed of light is a fundamental feature of space-time geometry, not just a property of light. This brings us to a profound realization. When we ask whether gravity travels faster than light, we're really asking about the causal structure of space-time. We're asking whether gravitational effects respect the light cone structure, the division of events into past, future, and elsewhere relative to any given point. And the answer, confirmed by theory and observation, is yes. Gravitational effects respect causality. The universe makes sense. Causes precede effects. Information can't travel backward in time or faster than light. But this is where things get philosophical. Why does the universe have this structure? Why is there a maximum speed for causality? Why is space-time four-dimensional with one time dimension and three space dimensions? Why does gravity exist at all? These are questions that physics can't fully answer, at least not yet. We can describe how the universe behaves, we can write down the equations, we can make predictions and test them. But why the universe follows these particular equations, rather than some other equations, is a deeper question that touches on philosophy, mathematics, and perhaps theology. Some physicists think the answer might be anthropic. We live in a universe with these properties, because these are the properties necessary for complex structures like stars, planets, and life to exist. In a universe where gravity propagated faster than light, or where space-time had a different structure, the laws of physics might not allow for stable atoms, let alone conscious observers asking these questions. This is the weak anthropic principle. The universe must have properties compatible with the existence of observers, because if it didn't, there would be no observers to notice. It's a tautology, but it's a tautology that might actually constrain what laws of physics are possible. The strong anthropic principle goes further and suggests that the universe must have properties that inevitably lead to the emergence of conscious observers. This is more controversial and starts to blur the line between physics and metaphysics. But regardless of why the universe has the structure it does, the fact remains that it does have this structure. Gravity propagates at the speed of light. Space-time has a causal structure. Information is preserved. The universe makes sense. And we're privileged to live in a time when we can test these ideas, when we can detect gravitational waves, when we can probe the nature of space-time itself and confirm or refute theories about how reality works at the deepest level. Let me bring this back to something personal and visceral, something that connects to your lived experience and makes you feel the weight of what we've been discussing. Every relationship you have with another person is mediated by the speed of light. When you look at someone, you're seeing them as they were a few nanoseconds ago, the time it took light to travel from them to your eyes. When you talk to someone on the phone, there's a delay, usually imperceptible, while electromagnetic signals travel through cables or bounce off satellites. These delays are tiny in everyday life, but they're real, they're fundamental, and they shape the structure of your experience. When you look at the stars at night, you're looking into the past. The light from the nearest star beyond the sun, Proxima Centauri, left that star 4.24 years ago. You're seeing it as it was 4.24 years in the past. If Proxima Centauri exploded right now, you wouldn't know for 4.24 years, and not just the light. The gravitational effects of its explosion wouldn't reach you for 4.24 years either. The moon you see is 1.3 seconds in the past. The sun you see is 8.3 minutes in the past. When you look at the Andromeda galaxy, you're seeing it as it was 2.5 million years ago, before humans existed. There is no universal now. There's only your now, the immediate present moment of your experience. Everything else is either in your past light cone, events that have already influenced you, or in your future light cone, events that you could potentially influence, or elsewhere. Events that are space-like separated from you, and cannot influence you, nor be influenced by you, at least not yet. This is the structure of space-time. This is what it means that gravity propagates at the speed of light. It means the universe has a built-in delay between cause and effect. It means information takes time to propagate. It means we're all isolated in our own light cones, connected to the rest of the universe by signals that take finite time to arrive. And yet, we're not really isolated. We're connected through space-time itself. The curvature of space-time at your location encodes information about the mass and energy distribution throughout the universe, weighted by distance and time. You're feeling the gravitational effects of the sun, the moon, the planets, the galaxy, even distant galaxy clusters. These effects took time to reach you, but they're here now, shaping the space-time you're moving through. You are literally moving through a four-dimensional geometry shaped by the entire history of the universe. Every massive object that ever existed has contributed to the curvature of space-time, and that curvature has propagated outward at the speed of light, shaping the geometry you're experiencing right now. When you stand on Earth, the weight you feel is you being accelerated away from your natural geodesic through space-time. You're trying to fall, to move freely through curved space-time, but the ground is pushing you up, forcing you off your natural path. This is what weight feels like from the perspective of general relativity. When you jump, you briefly move along a geodesic, falling freely through curved space-time. For a moment, you're weightless. Then the ground catches you, accelerates you upward again, and you feel weight once more. This might seem like a weird way to think about ordinary experience, but it's actually more accurate than the Newtonian picture of gravity as a force pulling you down. There is no force pulling you down. There's space-time geometry, and you're moving through that geometry, and the ground is in your way. The fact that this geometry is shaped by the mass of Earth, and that changes in this geometry propagate at the speed of light, means that you're connected to the cosmos through the fabric of space-time itself. You're not separate from the universe. You're embedded in it, shaped by it, moving through it. And when you understand this, when you really internalize what it means that gravity is space-time curvature, and that this curvature respects the cosmic speed limit, it changes how you see yourself in the universe. You're not a separate observer looking at the universe from outside. You're part of the universe, made of atoms that were forged in stars, living on a planet held in orbit by space-time curvature, experiencing consciousness through electrochemical processes that ultimately depend on the laws of physics that govern space-time itself. The question, does gravity travel faster than light, isn't just a technical question about propagation speeds. It's a question about the structure of reality, about causality, about connection and separation, about what it means to be a localized entity in a universe with a finite speed of information transfer. And the answer, that gravity respects the cosmic speed limit, that information can't travel faster than light, means that the universe has a certain kind of coherence. Causes precede effects. Events unfold in an orderly way. The past influences the future, but the future doesn't influence the past. Time has a direction, at least at macroscopic scales. This might seem obvious, but it's not. In the equations of physics at the microscopic level, time is reversible. The laws of quantum mechanics and even most of general relativity work the same whether time runs forward or backward. The arrow of time, the fact that we remember the past but not the future, that entropy increases, that causes precede effects, emerges from statistical considerations and boundary conditions, not from the fundamental laws themselves. The fact that gravity propagates forward in time at the speed of light, not backward in time or instantaneously, is part of what creates the arrow of time in general relativity. It's part of what makes the universe make sense in the way we experience it. Without this structure, without the constraint that gravitational effects propagate at the speed of light, the universe could be a chaotic mess of circular causality, effects preceding causes, information traveling backward in time. But it's not. The universe has order, structure, causality, and the speed of gravity is part of that order. Let me tell you about the future of gravitational wave astronomy and what we hope to discover about how gravity propagates in the next few decades. Right now, LIGO and its European counterpart, Virgo, can detect gravitational waves from black hole mergers and neutron-star collisions within about 1 billion light-years. That sounds like a lot, and it is, but it's only a tiny fraction of the observable universe, which extends about 46 billion light-years in all directions. Next-generation gravitational wave detectors are being planned that will be much more sensitive. The Einstein telescope in Europe and Cosmic Explorer in the United States will have arms up to 40 kilometers long, compared to LIGO's 4 kilometers, and will use advanced technologies to reduce noise. These detectors will be able to detect black hole mergers out to the edge of the observable universe. They'll see thousands of events per year instead of dozens. They'll be able to determine the parameters of merging black holes with exquisite precision, testing general relativity in the strong field regime better than ever before. But the really exciting possibility is space-based gravitational wave detectors. LISA, the Laser Interferometer Space Antenna, is scheduled to launch in the 2030s. It will consist of 3 spacecraft in orbit around the Sun, separated by 2.5 million kilometers, forming a giant triangular detector in space. LISA will be sensitive to much lower frequency gravitational waves than ground-based detectors, opening up an entirely new window on the universe. It will detect supermassive black hole mergers, millions to billions of times the mass of the Sun, colliding when galaxies merge. It will detect compact binary systems throughout our galaxy. It might even detect the gravitational wave background from the early universe. And there are proposals for even more ambitious detectors. The Big Bang Observer would specifically target primordial gravitational waves from inflation. If successful, it would give us direct observational evidence of quantum gravity effects in the early universe. With these detectors, we'll be able to test whether the speed of gravitational waves is exactly equal to the speed of light, or whether there are tiny deviations. We'll be able to search for evidence of massive gravitons or modified gravity theories. We'll be able to map the universe using gravitational waves and compare that map to what we see with electromagnetic telescopes. We'll also be able to do something called multi-messenger astronomy, where we observe the same event with both gravitational waves and electromagnetic waves. The neutron star merger observed in 2017 was the first example of this, and it was incredibly productive scientifically. By comparing the arrival times of gravitational waves and light from the same event, we can test whether gravity and light travel at the same speed to incredible precision. Any difference would show up as a time delay that depends on the distance to the source. The 2017 event constrained the difference to be less than 1 part in a quadrillion, but future detections will do even better. We'll also be able to test whether the speed of gravitational waves depends on their frequency. In general relativity, all frequencies should travel at the same speed. But in some modified gravity theories, there can be dispersion, where different frequencies travel at slightly different speeds, like light traveling through glass. If we detect dispersion in gravitational waves, it would be evidence for physics beyond general relativity. It would tell us that gravity is more complicated than Einstein's theory suggests, and it would point the way toward a more complete theory. We'll also study how gravitational waves propagate through matter. Do they interact with dark matter? Do they scatter off large-scale structures in the universe? Are there regions of space where gravitational wave propagation is different due to exotic states of spacetime? These are questions we can't answer yet, but we'll be able to address them in the coming decades as gravitational wave astronomy matures. There's also the possibility of detecting gravitational waves from exotic sources we haven't imagined yet. Every time we've opened a new window on the universe, whether it's radio astronomy, X-ray astronomy, or neutrino astronomy, we've discovered unexpected phenomena. Gravitational wave astronomy will likely be the same. We might detect gravitational waves from cosmic strings, hypothetical one-dimensional defects in spacetime left over from phase transitions in the early universe. We might detect waves from primordial black holes if they exist. We might even detect waves from regions of the universe undergoing quantum gravitational effects that we can't currently predict. The point is that we're at the beginning of a new era in astronomy. For the first time in human history, we can observe the universe through the geometry of spacetime itself. We can watch spacetime ripple and bend and carry information about the most violent events in cosmic history. And all of this is possible because gravity propagates at a finite speed, carrying information in the form of waves that we can detect. If gravity were instantaneous, if it didn't propagate, none of this would be possible. We'd be stuck with the static curvature of spacetime, unable to see the dynamics, unable to watch events unfold in real time. The finite speed of gravity is a gift. It means the universe is observable, understandable, predictable. It means we can learn about distant events by watching the ripples they create in spacetime. It means the cosmos is telling us its story, and we're finally learning to listen. Before we wrap up, I want to address one more question that might be nagging at you. If gravity propagates at the speed of light, and if this has been confirmed by observations, why do you still see articles and videos claiming that gravity might be instantaneous or faster than light? The answer is that there's a lot of misinformation out there, and some of it comes from misunderstanding legitimate scientific debates. Let me clarify a few points. First, there are legitimate debates about modified gravity theories and whether the speed of gravitational waves could differ from the speed of light under certain circumstances. But these debates are about small corrections or exotic conditions, not about overturning the basic result that gravitational waves propagate at approximately the speed of light. Second, there's confusion about what it means for gravity to propagate. As we discussed, the static gravitational field is just the geometry of spacetime. It doesn't propagate. Only changes in that geometry propagate as gravitational waves. Some people misunderstand this and think that because planets orbit based on the local geometry, gravity must be instantaneous. But as we've seen, this is wrong. The local geometry encodes velocity-dependent terms that account for the finite propagation speed. Third, there's a persistent misunderstanding of general relativity based on Newtonian intuitions. Newton's theory did have instantaneous gravitational action, and it worked well for most practical purposes. Some people think this means instantaneous action must be fundamentally correct, and that general relativity is just a small correction. But this gets the relationship backward. General relativity is the more fundamental theory, and Newtonian gravity is an approximation that works when gravitational fields are weak and velocities are low. Fourth, there are quantum mechanical effects like entanglement that seem to involve faster-than-light correlations. Some people conflate this with gravitational propagation, suggesting that if quantum mechanics allows non-local correlations, maybe gravity does too. But as we discussed, quantum entanglement doesn't allow faster-than-light communication, and it doesn't violate causality. The same is true for gravity. Finally, there's the problem of popularization. Science journalism often oversimplifies or sensationalizes results to make them more dramatic. A paper proposing a small theoretical correction to general relativity might get reported as scientists discover gravity doesn't obey Einstein's rules. when the reality is much more nuanced. So if you see claims that gravity travels faster than light, be skeptical. Look at the source. Is it a peer-reviewed paper in a reputable journal? Or is it a blog post or YouTube video? Is the person making the claim a working physicist with expertise in general relativity? Or are they someone with an axe to grind against mainstream physics? The scientific consensus, based on both theory and observation, is clear. Gravitational waves propagate at the speed of light to within the limits of our measurement precision. This has been tested directly with a joint observation of gravitational waves and electromagnetic waves from the neutron star merger in 2017, and it's consistent with all other observations of gravitational effects in the solar system and beyond. Could this consensus be wrong? In principle, yes. Science is always open to revision based on new evidence. But the evidence would need to be extraordinarily strong to overturn a result that's been confirmed by so many independent observations, and that's so deeply embedded in our theoretical understanding of spacetime. The beauty of science is that it's self-correcting. If gravity did travel faster than light, or if there were exotic circumstances where it behaved differently, we'd eventually discover that through careful observation and measurement. The universe is what it is, regardless of what we think or want. Our job as scientists and as curious humans is to figure out what the universe is actually like, not to impose our preconceptions on it. And right now, everything we know points to gravity respecting the cosmic speed limit. It's a beautiful result, deeply connected to the structure of spacetime, the nature of causality, and the fundamental laws of physics. So let me bring this all together and give you the final answer to the question we started with. Does gravity really travel faster than the speed of light? No, gravity does not travel faster than light. Gravitational waves, which are ripples in spacetime, carrying information about changes in the gravitational field, propagate at exactly the speed of light. This has been confirmed by direct observation and is a fundamental prediction of Einstein's general relativity. But that simple answer doesn't capture the depth and richness of what we've learned. The question itself is based on a misunderstanding of what gravity is. Gravity isn't a force propagating through space. It's the curvature of spacetime itself. Objects don't respond to distant masses pulling on them. They respond to the local geometry of spacetime at their location. When we ask about the speed of gravity, we're really asking about how changes in spacetime geometry propagate. And the answer is that these changes propagate as waves at the speed of light, respecting the causal structure of spacetime. This means several profound things. First, it means the universe has a built-in speed limit for causality. Information cannot travel faster than light, whether that information is carried by electromagnetic waves, gravitational waves, or any other means. This preserves causality and prevents paradoxes. Second, it means that objects in stable orbits are responding to the local spacetime geometry, which automatically accounts for velocity-dependent gravitomagnetic effects. This is why planets don't spiral into the sun due to gravitational aberration. Third, it means gravitational waves are a real phenomenon that can be detected and studied, opening up an entirely new window on the universe. We're living in the first generation of humans who can observe the cosmos through gravitational radiation. Fourth, it means spacetime is a dynamical entity, not a static stage. Spacetime can bend, warp, ripple, and carry energy and information. It's as real and physical as any other field in nature. Fifth, it means that our intuitions based on everyday experience and Newtonian physics are misleading. The universe is stranger than it appears. Space and time are unified into spacetime. Simultaneity is relative. Mass curves spacetime. Black holes exist. Gravitational waves ripple across the cosmos. And finally, it means we're part of an ongoing scientific revolution in understanding the nature of reality. General relativity is not the final theory. We know it breaks down at singularities and doesn't incorporate quantum mechanics. The next generation of theories, combining quantum mechanics and gravity, will likely reveal even stranger truths about the universe. But for now, we can appreciate what we know. Gravity propagates at the speed of light. Spacetime has structure. The universe makes sense. And we're privileged to live in a time when we can test these ideas and explore the cosmos in ways that were impossible for all previous generations of humans. The question, does gravity travel faster than light, has taken us on a journey through Newton's mechanics, Einstein's relativity, quantum field theory, black holes, gravitational waves, and the deepest questions about the nature of space, time, and causality. And the answer, while simple in one sense, opens up vistas of understanding that are breathtaking in their scope and beauty. The universe is more wonderful than we imagined, more coherent in its structure, more elegant in its laws. You now know more about gravity than most people will ever learn. You understand that gravity isn't a force, but space-time curvature. You understand that this curvature propagates at the speed of light through gravitational waves. You understand why planets don't spiral into the sun. You understand how gravitational wave astronomy works and what it can teach us. You understand the connections between gravity, quantum mechanics, black holes, and the arrow of time. This knowledge changes how you see the universe. When you look up at the night sky, you're not just seeing distant lights. You're seeing the past, light that left those stars years or millions of years ago. You're also experiencing gravitational effects that took the same time to reach you, ripples in space-time created by those distant masses. You're standing on a planet held in orbit by space-time curvature, moving through a four-dimensional geometry shaped by the entire history of the universe. You're made of atoms forged in stars that exploded billions of years ago, scattering their contents across space, where gravity gathered them into new stars and planets. You're a way for the universe to know itself, to ask questions about its own nature, to discover the laws that govern its evolution. And one of those laws is that gravity, like everything else, respects the cosmic speed limit. Information takes time to propagate. Causes precede effects. The universe has order and structure. This is what physics has taught us. This is what centuries of careful observation, mathematical reasoning, and experimental testing have revealed. And it's magnificent. So the next time someone asks you whether gravity travels faster than light, you can give them the simple answer, no. But more importantly, you can share with them the deeper understanding of what that means, why it matters, and how it fits into the grand tapestry of our knowledge about the universe. You're part of a civilization that has figured out the basic rules governing space, time, matter, and energy. You live in an era where we can detect ripples in space-time from black holes colliding billions of light years away. You have the privilege of understanding, at least in part, how the cosmos works. And that understanding is empowering. It shows you that the universe is knowable, that through reason and observation, through asking questions and testing answers, we can uncover profound truths about reality. It shows you that human beings, despite our limitations, are capable of remarkable intellectual achievements. So yes, gravity travels at the speed of light. But more than that, we know it travels at the speed of light. We've measured it. We've tested it. We've built a theoretical framework that explains it. And we're continuing to explore its implications, pushing the boundaries of human knowledge ever outward. That's the real answer to the question. Not just the fact, but what the fact represents. Human curiosity, scientific rigor, and the breathtaking beauty of a universe that reveals its secrets to those patient and clever enough to ask the right questions. Thank you for coming on this journey with me. Thank you for being curious enough to watch a 230-minute video about the speed of gravity. Thank you for being part of a community that values knowledge, understanding, and the profound joy of discovery. If you enjoyed this, hit that like button. Subscribe to the channel. Share this video with someone who loves learning about the universe. and drop a comment telling me what blew your mind most. Was it gravitomagnetism? Gravitational waves? The black hole information paradox? The idea that spacetime might be emergent? I want to know what resonated with you. And remember, every time you look up at the stars, you're looking into the past. You're seeing light and feeling gravitational effects that took time to reach you, traveling at the cosmic speed limit, carrying information about distant worlds across the vast expanse of spacetime. You're connected to the universe through the fabric of reality itself. And now you understand a little bit more about how that connection works. Keep looking up. Keep asking questions. Keep learning. The universe has so much more to teach us, and we're just getting started.